Okay, that's weird. So there are like two big topics in 7.1. What's the first big topic? Which technically for us as BC kids is what kind of concept? A review one, right? Yeah. So slope fields, technically review. Could we do a lot of AP practice on slope fields? Yeah. Definitely. But the problem is, what's part 2 of 7.1? Euler's method. It looks like Euler's, but it's not. Euler's is how you properly say his name, and I think German? I think. Euler's. Well, Euler's is how you properly say his name. I forget what his nationality was. I know his first name was Leonard. Leonard. Leonhard. Not just A-R-D, but H-A-R-D. Yeah, no, that's not. I'm pretty sure there were a lot more Leonards than there were Eulers. But anyway, coming back. Kind of like, oh, he's Swiss? Thanks. It's like Euclid. E-U-C-L-I-D. What was his first name? Leibniz. Do you guys remember that his first name wasn't it Wilhelm or something? Like, do you remember people's last names? Anyway, coming back. Rolle's theorem. What was his first name? No idea. Okay. Sure. Anyway, coming back. Euler's method. I had to think about how to say his name. Euler's method. We're not used to. Stop. I said it wrong. Euler's. Oh, this is horrible. There was a year that a kid literally made it like their life goal to get me to say it wrong all the time. And so he would keep on saying Euler's, and I'm like, sorry. And I was just telling you the wrong way to say it, and so of course I started saying it wrong. Anyway, Euler's method. Thank you. See? Oh, yeah. This guy. Nice thing is the AP doesn't grade us on pronunciation, thank goodness. Anyway, so, Euler's method. You guys see it's a numerical approximation? So it uses numbers to approximate. But numerical doesn't necessarily mean numbers. You guys know that there are 4 different ways, back to pre-cal or algebra or whatever, 4 different ways of presenting math, right? There's numerically, algebraically, graphically, I forget the order, and then verbally, yeah? You have words, you have graphs, you have numerical is like tables of data or statistical data. And then you have algebraically with an equation. And so numerical approximation is allowing us to some extent avoid the algebraic part of integrating and anti-deriving. We saw yesterday, at the very end of yesterday, I think you guys got to take that page down. We'll come back to the forever card. That instead of using a single tangent line, wait, in BC, what is this called? Using a single tangent line to approximate a removed point. Linearization or linear approximation or tangent line approximation. Or the AP could just say, use the tangent line. Oh, okay, fine. The tangent line. But what we talked about yesterday is if we want to get over to B to approximate, is that one tangent line at the point that we know, hey, remember when we were doing linearization, I could ask you things like the square root of 123 and you could get stinking close? Why? We know square root of 121. Sometimes there are particular points of tangency that you would use because you know it exactly. Does that make sense? So you're like, well, if you want to get to 127, no big deal, just use the square root of 126. I don't know that. That's not going to help. I need to use the square root of 121, but it's a distance away. Does that make sense? So, if I'm trying to get to not 123, but like 127, or even worse, something like, I don't know, 139. That's okay, just pick a better one. Oh, 144, I guess that's kind of close. Hold on. I guess those are all kind of close. But anyway, if you were to pick something that was like an equal distance away, so one wasn't necessarily better than the other, is there a better way to go than to use the tangent line that's quite a distance away? And the answer is yes. But to do that, we have to start at the exact point we do know. Hey, check it. Did you guys see yesterday that I said f of x sub naught equals y sub naught? It's the one that I know is equal to. We start at a point that we know. We start at a point that, like square root of 121, we have the precise exact answer to. It's usually given to us, though. It's not a big deal. Actually, I should put it down here. They're usually giving us the point, the original point, the initial point to start at. So we could add that to our given information. They usually give us a starting point, a differential equation, and some sort of step. Check it. Where did the approximate signs start showing up? Where did the approximate signs start showing up? You see it? As soon as we leave the point of tangency. Do you see it? Point of tangency, right there. As soon as we leave it, okay, but that makes sense. As soon as we step away from the one that we know, there's going to be a little bit of error. But the point is that we're not trying to step from A directly to B. We're trying to take babier steps, smaller steps, and say, okay, your tangent line's good for a little bit. We better recalibrate a little bit. We've gotten off, let's recalibrate. Okay, now let's head this way. We're getting off again, let's recalibrate. Let's recalibrate. And as you guys saw in the picture yesterday, if you were tracking with what was going on, this recalibration is reassessing the slope. At this point, the slope is, yes, but it's not staying that way, it's a curve. It changes as soon as I move away from my A or my X of that. So let's move for a little bit because, okay, we don't want to take like infinitely many steps. It's going to take forever. This is an approximation technique, so we are going to go ahead and get a little bit off. That's okay. We're going to take a step and say, okay, but wait a minute. Here, at this point, what's your slope? Oh, let's use your slope now. Let's forget him. Let's use your slope. Sweet. Your slope. And we'll move H again. And then we'll recalibrate and say, what's your slope at the curve? Oh, okay, let's use your slope. So we're going to have our tangent kind of like baby tangents, but not in a slope field way. Maybe you guys are seeing why they have these two topics in one section. We're using baby tangents that are attached to each other. And to be honest, probably are a bit longer in this Euler's method than it was in slope fields, because those are just little slivers all accumulated to show flow. But in these ones, I'm going out a certain distance and then recalibrating. But what I'm recalibrating is the slope. Now, pause. Will this second line go through this first point? Will this second tangent line go through this first point? No. Is this actually a tangent line? No. Because it's not skimming the curve, is it? So it is going through the point at which I'm leaving the tangent line. I'm going to use this point for this line's point, but just use the derivative for its slope. And then I'm going to have to use, once again, this point for the next line, just stealing that slope. Because once again, the dilemma is I don't know exactly where it hits the curve. The point is I only knew this one, but I can move by lines up and out. Okay, this whole process of you can't use the original point, that's a bummer. You can't use the original slope, that's a bummer, leads us to this whole process that you guys are seeing kind of happening over here. You're given some sort of first order differential equation. Probably, I guess it could be a second or third order, I suppose. But we'll just say given a first order differential equation. An initial point, they have to tell you something about how to start, and it has to be exact or else you're in trouble before you start. Some exact point of tangency on the function itself, some value that you do know. Some sort of way of progressing forward. Maybe they tell you, move by 0.1s. Okay, fine, we'll move by 0.1s. Maybe they say, go from 2 to 7 in 3 equal jumps. You're like, okay, I can do that. 2 to 7 is a distance of 5. Ew. That's going to be a gross jump. But you could. You could do 5 thirds. I'm going to jump 5 thirds, 5 more thirds, 5 more thirds. In 3 steps, you will get there. So it's not always them telling you exactly what the jump is. They might just tell you how many steps, and you have to figure out like the difference, like we do with Riemann sums. Or maybe they just tell you literally go by 0.5s, go by 0.1s. And you can approximate the y values of f of x using this numeric process. You start by rewriting the initial point given up above. You start by rewriting the initial point given up above. F, throughout the process, is going to represent the actual function value, which is why I'm allowed to have an equals to start. Because because I know that one. F of x sub naught is y sub naught, they told me. But as soon as I get to f of x sub 1, which is h away, I've gone forward to a new x value, either using the h that they said or using the step that I figured out. I've gone to a new x. I am on my tangent line, which means I'm a little bit off. But I'm using that a little bit off to approximate, hence why there's an approximate, to approximate this next function value. But some of you are like, what on earth is this? Well, let's talk about that. Didn't we say that we've used a single tangent line to approximate before? And that single tangent line, wasn't it an L of x is approximately, right? Well, actually, I shouldn't say that. I should say we could have done something like, oh, that's a random yellow, okay. I could have gone straight to B using the linearization, which would have, do you guys remember what L of x stands for? Isn't it like the y and the y minus y1 equals n times x minus x1? Mm-hmm. L of x is that y, so what have they done to the minus y1? They've added it to the other side, so it's y1 plus, well then we have our slope, our n, but who's our m? Isn't it f prime of our x1 at x minus x1? Now hold on, wait a minute. What does that look like in context of this? Oh, hey, check it. It's a y. Hey, isn't he my differential equation? Isn't my differential equation going to give me slopes, right? Slopes times change in x's. And who's h? A change in x. It really is an application of a tangent line. Except in this case, instead of just using one point of tangency, x1, y1, and going straight to, well, hold on, wait a minute, we're trying to find b. So couldn't we make this particular and say, okay, hold on, we're trying to actually find L of b, not just L of any x. This is an equals because the linearization is the approximate. The approximate's right here. The linearization equals which approximates. And you would have your, in context of ours, our y sub naught plus our f prime of, we could put x sub naught and y sub naught because maybe our differential equation has x's and y's, it's implicitly stated. And then we could say our little delta x, which we could replace with h. Joe, sorry, you had a question.
Is this an never covered?
Yes. I know it's messy, but yes. Wait a minute, why is there a dot 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 at the bottom? It goes on however many jumps, however many steps you need to take. Maybe they say get there in 3, so you're done. Maybe they say get there in 10, so you're definitely not. But long story short, where are you ending? You are ending at whatever place or whatever function value they want you to approximate. Do I know where that is? No, because I have no idea how many steps you're supposed to take. I know the distance of the steps, or we're finding the distance, but I don't know how many steps. Is it 3? Is it 5? Is it 10? And you're just going to have y of x sub, well, do you guys realize that you're using the x from the one before and always going to jump to get to the next one, right? So the x sub n minus 1 plus h. You have made a jump to land here where you're ending. You're going to have an approximate because that was the whole point. This entire process is approximation. You're using the check it. You're not using the current y. You haven't found him yet. You're using the previous y, which will be y sub n minus 1. Once again, you haven't found the current approximate points. You have to use the previous x sub n minus 1, y sub n minus 1. And guys, you literally are just using, oh, well, that was an h. Awkward. You're using the previous point in order to plug in. I'm going to do one more color coding. I know I see some questions out there. Give me one sec. What I want to color code is, here we go. Doesn't Let me use green or something random like that. Green is light enough. You steal him by going back. You steal him by looking back. You steal him by looking back. You steal him by looking back. And then you land on your final approximation. This is a number. That's fine. 3. Oh, that was number 4. I must have split up a card last year. I didn't split this year. There were hands somewhere. I don't know where they are. Adrian.
What if the agent could call F of N
The problem is N represents in agreement sums how many, not where. Does that make sense? So at the very beginning, I'm thinking of this as like my F of A trying to get to my F of B. But I mean, we have snazzy notation. I'm not going to change that. But I'm thinking of B being my landing point, like an integral. You land at B. Because N is just saying, like, you got there in 3 or you got there in 5. And maybe you're at 17. So the 5 or the 3 wouldn't help. Does that make sense? Kevin.
So since we're learning like different approximation methods like linearization, Euler's, and like other ones from next semester, can there be like an AP problem similar to like how for Riemann sums it says to do L-gram and gram, and like for this it's like use linearization, use Euler's, use like
There theoretically could be. I haven't seen in my head to have that be an FRQ. You would need different parts probably, like an A being linearization, B being like Euler's method, C being maybe like a Taylor-Maclaurin polynomial from second semester. I haven't seen them dedicate an entire FRQ to solely approximation. So I don't think they would do that because that would pretty much be them dedicating the whole thing to approximation, and there is more that BC covers, so percentage-wise, I don't think they would do that. But I have seen Euler's be like a part B. Does that make sense?
Yeah.
But good question. Like it would be an interesting one to do. I just think as far as them thinking of the grand scope of the class, 1/6 of the information, yeah, I don't think they would. But they could, thinking of Riemann sums and tangent lines and all that jazz, we are going to have to think about over and under approximations for every new approximation technique we see, including Euler's. But the nice thing is, Euler's, hold on, what would determine, if you guys look at the picture again, oh sorry, wrong way. Euler's is built on what again? Ultimately, at the very beginning, what's it built on? A tangent line. So couldn't we say that Euler's is an over or an under approximation the same way we would say it for linearization or for a single tangent line? And how do we know whether a tangent line will fall below a curve or above a curve? Concavity. So Euler's is just going to be based on concavity, just like tangent lines are. We need to do one. Here we go. This one. This one. This one. Some of you guys are going to look at this and be like, dy dx equals y. We can anti-derive that. It's 1 over y dy is equal to dx. It's no big deal. I know. But we're just getting the idea down. Remember, almost any new topic in math, we choose a simple example first, yeah? And to be honest, this approximation isn't going to be great. Because do you see the step size? We're going by ones. Is there a lot of error that could happen going from 0 to 1? Now, not if you were doing like square root of 121 to square root of 122. You have a big value and there's like a big range between the square roots. I mean, 1 up there isn't going to make a big difference, but down here it might, depending on what this function is. And I'm going from 0 to 4, which is a big removal. Depending on the function, okay, I might not get there very precisely, but let's see. No matter what, I'm going to get there better than if I was to do a tangent line and then plug in 4. Okay, so let's see. Here we go. This is my f of xy, aka my differential equation. Are there x's in it? No. So could I technically say it's f of y? Yes, I could. It's just in terms of y. But no big deal, whatever, he's my differential equation. Okay? So if he's my differential equation, wait a minute. isn't this supposed to be my slope? Right? What part of this differential equation technically talks about slope? Just kidding. Euler's method, only first degree or first order differential equations. I just saw one. Where's the slope component in here? Y prime. So if possible, could it make my life a little bit easier if I get y prime by itself? Yes. So maybe it's a little bit easier to think about. Yes, this is the component, this is the piece that helps me find my differential equation specifically though. My slope clue is that y prime equals y, hence slope comes from the y value alone. Does that kind of make sense? We'll see. Where's my x sub naught, y sub naught? Oh, there he is. This is my point of tangency. This is my point of tangency. If I was to, this is not Euler's method, you can just watch or you can write down. If I was to find the approximate of y of 4 using a single tangent line, I would say no big deal. Plug in 4, 2. Let's see, I'd have to use my point of tangency, which would be y of 0 plus f prime of, technically I'm going to put 0, 1 because it kind of depends on the differential equation as to what you're plugging in. And then we have x, which is 4, minus the x value, which is 0. Then we would go ahead and say, oh, that's 1. Plug into your differential equation, guys. He says, give me the y, give him the y. What's the slope? 1. So I would say 1 times 4 minus 0. My approximate using a single tangent line would be 5. 1 plus 4. Single tangent line, done. Euler says, nope, you gotta jump. So we start with y of 0 equals 1. That's like f of x sub naught equals y sub naught in your forever card that you just wrote down. Step 1, I know this. I'm supposed to be stepping by 1, so I'm going to go from 0 to 1, from 1 to 2, from 2 to 3, and from 3 to 4. Which is technically, I mean, I could be using f of, they use y of, so okay, fine, I'll use their notation. This is going to be y of 0 plus my step size, y of 1 plus my step size. Not that you necessarily have to write this every time, but just reminding you that to get to the next one, we use the previous one. So we're jumping, we're adding an h to the previous x, to the previous x, to the previous x, and to the previous x. Okay. Now it's time for my approximate though. I need basically my linearization formula. And I get to start with the point that I know, which is exactly where my tangent line would start with. So I could say y of 0. Well, what is y of 0? 1. 1 plus. I need a slope. It's a tangent line, technically. So what's my slope going to be? It's going to be f of, except I'm just using the y's, right? So who is the old y? 1. Times, well, what's my h? Or what's my x minus, sorry, my 1 minus 0 or my delta x? What was my jump? Just 1. So then that would end up equaling, now I have an approximate, it's okay. My actual y is separated from this approximate with an approximate right there. That's going to be 1 plus, oh, that's going to be 2, right? Because what is f of 1? 1. And 1 times 1 is, oh, okay, no big deal. But for those of you guys who need to see it, I so apologize. That's 1 plus 1. Okay. But now you can build on that and say, okay, great, I went a little bit, and now I need to adjust. So I get to come down here and say, you're going to approximate using the y that we just found, which was 2. Now, according to the picture, this is where we are in our jump. We started at a point, oh, sorry. We started at the point 0, 1, which this picture is not. I know I need to make a picture where it is. We started at the point 0, 1. We've gone out a tangent line and said, hey, well, where would this land? Oh, it would land right there. I'm off the curve, but that's okay. I have a point that I'm going to use, and I'm going to recalibrate and adjust and go to a new tangent line. So, to go to the next tangent line piece, I'm using the previous y, the point that's a little bit off. And I'm going to add, now, the slope at 2. because I need the last one. Times, wait, well what was my jump in x? I just went 1 again, right? Okay, so then plug in 2. Oh, that's easy. Y prime is just y. So I have 2 plus 2 times 1, which will be 4. And now I go ahead and use my approximate and say, okay, 4 plus, you guys getting the pattern a little bit? So I can go ahead and say, oh, that's easy, it's just 4, so 4 plus 4 is 8. I can go to the next one, using the previous point, which is 8, plus f of 8 times 1 is going to end up being what? 8 plus 8? Why is this an easy example? Plugging into the differential equation just said use the y, and the step was 1, so I wasn't having to deal with any weird decimals of having to multiply by a half or 0.1 or anything crazy like that. So my Euler's method says his approximation is 16. What did my single tangent line say the approximation was? 5. And didn't I tell you guys this was an easy one? What would my calculus have said this was exactly? Ooh, we can do this one exactly. Yeah, we can. Can't we say dy dx is equal to y? So can't we say 1 over y dy is equal to dx? Can't we actually integrate this to say ln of y is equal to x plus c? Can't we take an e to the both sides? Ooh, do you guys remember the whole exponent rule thing? How addition of exponents is really multiplication? And then can't we plug in our initial point of 0, 1? So then if I plug in x is 0, making the 0 power is 1. Oh, c is equal to 1. So what's my actual function? F of x is equal to 1 e to the x. Wait a minute. So f of 0 was 1. Yeah, we already knew that because f of 0 is e to the 0, which is 1. What were they asking me to approximate? What's e to the 4th? Around 16, so it's 2.7. Well, higher because it's 2.7. 3 to the 4th is 81. Stink. What's that going to be? Yes, you're right. 54.598. I'm not rounding. Wow, 16 better than 5. But what did I warn you? What were our steps? For an exponential function? Come on, that's like the fastest, one of the fastest factorial growth is faster. One of the fastest types of growth. Like it gets really steep, really fast, and your line's like, ooh, I'm just trucking all my life. Right? Like, okay, we get it. It's off, but it was closer. Guys, you guys noticed? I don't know why he's there. Let's just get rid of him. The one. My number countries. You ready? The step of 1 gave us a lot of error. So what should we step by maybe instead? And let's do a function that you couldn't anti-derive. Remember, he's one of those that has a plus between the x and the y. He's impossible for you to anti-derive. You couldn't find the original function. Well, I mean, part of it is you can't find the original function to know whether or not you're close. But that's not the point. The point is, can you find the Euler's method approximation? Ready? Set? Do you want me to start you? Yeah, we just did it, right? It's not going to be hard.
Oh, wait, you have to do this all manual.
What's your first one? What's the next one?
2 plus.
Am I at 0.1 now? Yes, because I've started at 0 and I've gone how far? 0.1. And that's going to be, see my approximate? So what's this guy going to be? 0.2. I'm going to go another 1. What's the next guy going to be? 0.3. I'm going to go another 1. P.S. Write small. Where are they having me land then? If I'm taking 10 steps going by 0.1, what are they actually having me approximate? Oh, nice. The y prime is by itself. Ooh, he looks a little bit nastier though. There's an x and a y. Oh, and I have decimals this time. What was my previous point? 0, 2 times, what's my delta? X or my h? 0.1. Now, something that you might want to keep in mind for the rest of this problem. If you multiply by 0.1, don't you just move the decimal place 1 to the left?
Yes.
Just checking. 0 plus 2 is 2. 2 times 0.1 is 0.2. 2.2. Ah, this is easy. But now you have to use that 2.2. Now you have to use that 0.1 and the 2.2 with the 0.1. And now you have the 2.2 plus the, stink, the 0.1 plus the 0.2.2 is 2.3. And 2.3 is going to be times 0.1, which is going to be 0.23. And 2.2 plus 2.23 is 2.43. Roll me on the second one. I have to 0.1 plus 2.2 is 2.3 times 0.1, move the decimal place. 2.2 plus 0.23 is 2.43.
You're so right.
P.S. Get your calculators out. Because you can see I went from one decimal place to 2 decimal places. I'm only on the second one. Am I gonna go to 3 and 4 and 5? Oh, I'm sorry, guys. Thank you. Reminding me of my little lessons.
I know. It's on like on the C.
2.693. Anybody beat me there?
No.
Yes, I do. Nice. Oh, keep going. I'm not going to beat you. Silent assembly laugh. I'm gonna start running out of space. I'm gonna start doing it in my head. Sorry. That was a 9, right? Yeah. 2.993. Is that 0.2? $2.9923?
Yep.
Did I rewrite it right? 2.9923, right?
Yeah.
I just rounded to the straight.
I'm writing this down in examples. I'm doing
We're
this.
adding.
Party pooper!
Let's round to the
We're
whole
adding
number.
Let's see what
a
happens.
decimal time.
Dude,
It'd be like 2 and
There's so many. I actually
Why do you
have
so much
to, it can't do mental
okay.
math, I have to
Just
write
write
it down.
It's gotta be on the
Just say
same
excellent.
page.
Probably not 10 and probably not a 0.1. Probably like a 0.5 or a 0.2. And probably just like 3 or 4 steps.
And then the side variables on the left.
I didn't make a
I
calculator.
saw
I'm
the
like,
change.
well, only on
I listened.
whiteboard.
Into the picture. That's all lazy.
I'll just come and drop one.
Yeah, I saw
You guys are
English.
cool.
I saw picture.
No, he does my video.
3, 5, 11.
Can we like cut this part of the recording out so like Ryan has to do this by himself?
Yes.
No, I'm just
I didn't hear what you said.
Ah, 13, you guys.
No,
Give
I
me
just
that.
did
Being
the
distracted.
example.
No, 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 no. 11, carry the 1, that's 12. 3.33153?
Yes. 1? Okay.
I think, cause 9 and 2 is 11.
That is correct.
Oh yeah,
It's
that's
what?
What? What's happening?
I've said it
Good.
50 times.
I did it by calculator.
I got the
It's cause
exact
you
same
stole
thing.
my brain cells, that's why.
What? How did that happen? I don't know.
You could be like labeling that A and that B and that C and that D and that would save a little bit of time. They're really gonna be running out of space.
Close.
Okay, so 0.3.
You know, just like,
Alright, so we pick a marker.
Just 2 seconds ago you were questioning if the A's and now you're saying all the A's.
I speak British and Creole since I could appreciate.
Better and better.
3.714683?
What's the
Yes.
corresponding?
4-6 or 7-4?
714.
714.
Oh yeah, something happened.
Yeah, so if you guys are saying yes, say yes, stop.
I'm not.
I know, I'm just warning.
No.
You haven't been using a calculator this entire
No.
I'm not even bragging to experience.
He's home by horn. He's good.
So I need a thinner marker because I'm starting not to be able to see my numbers. Where am I at? Oh, 4. And 3. 1, 4, 6, 8. So it's 3 and 11. And a 1 is 14, so 15. And a 1 is an 11. And a 1 is a 6. 4.14615113?
Yes.
This is like the forbidden area of the
This is why
calculator.
you're a math teacher.
No, some of you guys are going way faster, but my thick marker's not helping.
We're doing it
Yeah.
by calculator.
And I would rather be like
You're
showing
doing
work,
it
but
What is this
by
for?
your head.
some people are doing it the long way.
Oh my, I think
Who's
I
doing it
see
the
what's
long way
going
still
on.
with me?
I don't
Oh,
really
you
know.
have to
Thank you.
Nice job,
Yeah, I know.
Oh, now Dana wants to do it.
Well, that's gonna be nice and easy.
Oh, that's gonna be nice and easy.
Definitely the cleaner version.
Well, that was easy.
Well, like, I don't have to carry the, I mean,
Right, like you know the buttons look there and you go, whoa, that was neat. That was easy.
that's gonna be
Nothing
Is
about
there any reason you want to show me that? They said the other
I understood it at Wi-Fi. I just don't know where we're going on.
Yeah, what's the
Really wrote that.
N equals 10, Christina.
No, it's not.
4.63076643?
Yes.
Yeah.
No, I used to be team captain for
Oh look, I'm right here.
whatever amounts Entertails.
What's the point of me doing a super, super long one?
To show how tedious
Hopefully
it's gonna get.
the repetition. No, well, just the repetition. Hopefully you're getting the process of look back, steal the point, plug it in. Look back, steal the point, plug it in. Look back, right?
Oh, I know it.
4.6. Do you think we're a little bit more precise this time?
Yeah,
Me
we're
too.
not painstakingly sad.
Well, sad thing is we can't. You could probably like Google it, go to Wolfram Alpha, and have them try to find a solution for you, and they could use something that's more precise. But you would plug in a differential equation and ask for the solution at 4. So you have to carry the 1. That's me 14 and 1 is 55. So 55, 4, 0, 7, 6, 5. 1 again. 0, 6. So 6, 0, 7, 3, 8, 4. Which will approximate y of 1.
Just do the rectangular A.
3, 0, 8, 3, 7, 12, 11, 8. 5.7812273803.
Yes.
Woo! That was fun. What made this able to be done by hand? For like most of you, you could have done it if you had just taken time.
Yeah.
Point 1. Point 1. What would have been harder? 0.001. Actually, that's not too bad. Just 2 decimal places. How about like 0.2?
Yeah.
Because 0.2, would you be able just to move the decimal place once? No. Okay. Could Euler's method be a calculator problem on the exam?
Yes.
It could, except don't you think there's a way to program this rote repetition or this somewhat annoying repetition in a calculator? Yeah, definitely. And think about the AP exam. Are there ways to do Riemann sums in calculators? So what do they do? Put it on the non-calculator portion, or do something with unknown information that you can't plug into a program. Guess what they're going to do with Euler's also? Put it on the non-calculator portion, or not give you enough information to be able to put it into your calculator. Okay, so then pause. What does that mean about how hard the math will be? It won't be hard at all. But what will be important? The process. And the process, well, can you guys remind me of what I did? What did I do? Did I start writing approximate as soon as I moved away from the point? Yes. And what was there at the very end as well? Okay, if you don't have that, they take off a point of your hopefully hard-earned solution. Don't do that. Then what? What was I using every single time to plug into my differential equation, which was my slope and my linearization? I was using the previous point, right? Every single time? The previous x and the previous y. True? Or the approximate of the y. So I'm not on the curve past this original point. Remember, I'm a little bit off, but then I'm trying to recalibrate and recalibrate and recalibrate. I'm assuming, I'm increasing somehow. So the lines are getting steeper and steeper and steeper, as shown by the slopes getting higher and higher and higher. Not very high, it's more like this. So I'm going back every single time. What am I multiplying? Well, hold on. Don't I have to, I don't even know. You guys get the pattern, right? How am I doing this? Because these are slopes. What was I doing? What else made it easy? I just had to add them. What if it was a 3x minus y? Okay, so I had to plug in to get my slope. Once I got my slope, I had to multiply by the h. It was very nice that it was a 0.1. And then I had to go ahead and get my final approximate. And I'm slowly just building up to that final spot. Long story short, all of these 10 steps is a lot more exact than going straight there on one line. How much more exact? I don't know. See if you can figure out what the actual f of one value would have been for the differential equation x plus y. I bet you could within a certain degree of accuracy. Alright, cool kids, with that, you have 30 seconds. It was fun. Euler's method. Come here.
How did you do that?
Do some
It's more like an English.
I don't know if I gave you a 10-step one. Doing me, I might have given you one, probably not two.
Ryan, are you on Tuesday?
No.
Oh, so that's why Melanie asked.
Why would I do it?
Yes, I'm getting more copies. I forgot to have enough for BC too, but I do have new stamp sheets. If someone's planning on getting a stamp today, come up and grab it. Otherwise,
Oh.
I'm going to get a stamp today. Come grab it. If you haven't turned in your stamp sheets by the end of the day, please. I get it. Thanks.